All right. Thanks everybody for coming to the UTIG discussion hour this week. This week we have Alex Miltenberger with us here. He's a PhD student at Stanford in the Department of Geophysics. He got his bachelor's from Michigan Tech in applied geophysics, and he's now working on landscape dynamics, subsurface geophysics modeling. So he's going to tell us a little bit about it.
Yeah, thank you for the introduction. I'll get my screen up here really fast and then we can get going. Yeah, a sec. There we go. Okay. So are you seeing my presenter mode or?
Yes, we're in the presenter view.
Off then. Here we go. Okay. So yeah, I guess first of all, thanks to you guys and to Jay for setting me up and having me here to present to you guys. And I'm excited to be talking about this because this is actually the work that I'm sharing with you guys today. This is kind of the first time I've really been able to share this with like an external audience. And this has been kind of the culmination of some work we've been thinking about over the past 3 years or so. And it's really been starting to take shape. So I'm excited to share it with you guys and to see what you think. So, you know, I'll encourage people to interrupt me if they have questions. I'll try to make a couple of pauses so it's not so much me just dragging on. But the purpose of the work that I'm presenting today, we're calling it hypothesis-driven geophysical inversion because we're interested in a specific type of, or a specific use case of geophysical inversion. So to illustrate the problem, I wanted to share this picture with you guys from one of the field sites that we've been working at in Colorado. The purpose of this study specifically was to look at groundwater flow pathways. But what we did is we went out and we collected electrical resistivity tomography data along this black transect here. It goes down the flank of this valley, over the river, and then up the other side. And so that's what you can see here. This is the inverted resistivity data from that cross section. And what really struck us was this anomaly, this really conductive anomaly down here in blue. And when you look at it on the surface, there doesn't really look like there's anything there. So, you know, we had a big question is because we're interested in groundwater flow paths, we were interested in what could this be? And so this is the kind of question that we're focusing on in this talk here. Just to give a little more context about how we're thinking about these types of problems. So if we just consider like the applications of geophysical data along a spectrum, on one hand of the spectrum, we can consider cases where we have little to no prior knowledge and we want to learn something about the specific area. And then on the other hand, we could have like a lot of prior knowledge. We could target our geophysical survey to learn something about the subsurface given what we already know. And an example of not having a whole lot of prior knowledge, this could be like exploration. So this could be we are going, we're looking for natural resources or whatever, and we can go collect a bunch of seismic data and just invert that seismic data to get a sense of the big picture, what's going on, what are the structures, what basic geology are we working with in this area. And the main tool for working with geophysical data in this context is inversion. So, we take our data and we do an inversion and we can, learn something about, just get a map of something in the subsurface. Now, on the other end of the spectrum, a good example is a lot of like scientific studies. So this is an old one, but I think it's a really classic example of, going out and collecting geophysical data with a purpose. And so the purpose this example here was to go look at seafloor spreading with the magnetic anomalies. And so, by going out and collecting these the magnetic data, and so we can learn something about the process of what's going on with the crust or other parts of Earth processes. And so this application, we're going to kind of loosely refer to it as a hypothesis testing application, where we go out, we have prior knowledge, and we go out and we collect data to test that hypothesis that we've come up with based on what we see in the geophysics. Somewhere in between, we have this gray area. A good example of this is the characterization problems, where we've maybe already gone out and we've collected the data, or we have data and we are interested in pulling out like a few key parameters of that data. And this is used all over the place. So this, for example, this is an example from our own work where we're interested in these buried paleo valleys. And so our goal in this work is to take airborne EM data and go out and pull out like the dimensions of this paleo valley. And so this is somewhere in between, and we're going to call this hypothesis-driven inversion because we know what's under there, we know our target, and we want to invert the data for a few specific parameters. And so a big problem when we're working with these types of problems is uncertainty. The uncertainty quantification is obviously a massive topic, but in the broadest sense possible, the biggest tool that we use is Bayesian inference. So in the inversion context, the way that we're handling uncertainty is we write this probability distribution. It's a conditional probability of our model parameters given our observed data. And if we put symbols to it, we can say that's the probability of M given D, where M is the model parameters and D is the data. And so then the challenge is to just go and calculate this probability density here. For hypothesis testing, it's similar. We can write hypothesis, the posterior probability of hypotheses as P of H given D, where H is our hypothesis and D is our data. And the main tool that we have for calculating these posterior probabilities is Bayes' rule, which is just shown here, just a rearrangement of this conditional probability in a different form that we can work with. So in the geophysical context, the challenges that we have is that our data are really high dimensional. We have like thousands of measurements in seismic surveys. We could have like millions of measurements or even more. I don't even know what kind of data sets people are working with these days, but they're massive. So it's really hard to work with them. The other challenge is when we're doing uncertainty quantification, we have these computationally expensive forward models. So even if it takes like a couple of minutes to do a forward model, when you need thousands of samples, that adds up really fast. And in practice, the main way that we solve these is, and this is again, a massive topic. I could never go through all of the different solutions to this inverse problem. But the main one that we see used in practice for uncertainty quantification is sampling methods. And so what this means is we write our posterior distribution as this proportional to the product of a likelihood function times prior. And so, this is, used in all sorts of uncertainty quantification methods. And this is, how we formulate inverse problems. And I'll talk about how we actually do the sampling in a second, but hypothesis testing is similar. We write the hypothesis testing problem in terms of this Bayes factor. This is one way to do it. There's other ways to do it too. But this will be important for us later, is to know the Bayes factor. So the Bayes factor, we just write as the ratio of the data given the hypothesis for two hypotheses. It has to be two hypotheses because it's always relative to something when we're doing hypothesis testing. And so the intuition here is, if it's more likely to observe the data under the first hypothesis, then that will be a greater probability than observing the data under the second hypothesis. And if that ratio is greater than or less than 1, we can make some arguments about which hypothesis is better. And so yeah, B is the Bayes factor, and then these are the ratio of our evidence terms. So now in practice, when we need to account for uncertainty, what we do is we expand this ratio using a technique that's called marginalization, but really it just means we introduce this probability of we introduce this model parameter term to account for uncertainty in our model. And the important thing here is to just note that this on both sides, both the numerator and denominator, it includes this likelihood function and a prior. So the inversion and hypothesis testing problem essentially go back to the same type of setup. And we use, whenever we see likelihood times prior to get a posterior, we end up using Markov chain Monte Carlo sampling. And so for those who may not be familiar, or maybe loosely familiar with MCMC, it's a random walk. We walk through our space randomly, and we accept or reject our model based on some criteria. And the idea is if we do this long enough, then we get a posterior distribution, or we get samples from a posterior distribution at the end of it. And then from those samples, we can calculate probability for different parameters, for different hypotheses. We can do all sorts of stuff once we have those samples. But there's challenges with MCMC. And anyone who's ever tried to do this, it will be familiar with some of the challenges with MCMC. And really it all boils down to this problem with convergence. So when you do MCMC, one way to view convergence is to make a plot that looks like this. So this on the x-axis, this is the number of iterations that you do in your random walk. And then the y-axis is the acceptance ratio. You can think of the number of times we accept a model versus the number of times we reject a model. So you have the stair-step behavior. You have rejections before an acceptance, or vice versa. So you get this kind of stair-step behavior. And then one way to view these plots is to look at different phases of your sampling. First phase, we call the burn-in phases, where we initialize, like we don't know where to start, so we just have to start somewhere in random walk, and then we just have to let the random walk kind of roam around until it finds a good place. It finds a point actually sampling from the distribution that we want to sample from. This is called the burn-in period, and in practice, this means is we have to throw these models out that aren't representative of the true posterior distribution. But then once we've finished that burn-in period, we can sample from the posterior, and if we do that long enough, then we reach convergence. But the challenges with this when we're working with geophysics is that our models, again, can be expensive to run. So we have to throw them. We have to throw all of these models away. We have to throw away the burn-in period. And if we want to restart, we have to redo this burn-in period again. If we have a low acceptance rate, we're going to throw away a bunch of our forward model realizations just by nature of MCMC. There's no way around it. A good acceptance rate would be like 0.5. So if you're throwing away half of your models and keeping the other half, and still, doing a good job of your sampling, then that would be like probably best case scenario. So best case scenario is we're almost throwing away half of our models when we're using MCMC. You have problems with having to run this serially. It can be hard to parallelize this, although there are implementations. And then the final difficulty is when you have multimodal distributions, you can get stuck in these local modes. So just to illustrate, this gray is if we have a true distribution, what can happen is if we don't tune things correctly, we can get stuck in this mode here and completely miss this part of the posterior, which could be important. Now, all of this is not to say that there's no ways around any of these problems. There are. This is a massive field. There's like a ton of literature about how to handle all of these different challenges. But the main point is that when we're working with geophysical data, again, high dimensional data, computationally expensive forward models, it can be really hard to do this. It just is, even with the most advanced tools. And so what would be great is if we could go from our prior model to just pull out those few parameters that we're interested in and the types of problems that we're talking about here, and just pull out the posterior distributions without going through the sampling. So what if there was a way that we could just go, not have to worry about sampling the posterior and just calculate posterior distributions directly? And so that's going to be the focus of the rest of this talk here, is how we do that. And it turns out that the way to do that is going to require us to kind of rethink how we approach inverse problems in the first place. So we're going to introduce this different way to formulate inverse problems. We're going to call this probability intersection theory. It's been around for like 40 years, actually, but the applications are pretty minimal. And there's good reasons for why it's not used a whole lot in practice. But I think some of the advances that we're going to show in the next half hour or so can show that this theory is actually really powerful and can help us solve inverse problems in ways that we haven't been able to solve them before. So I'm going to change gears a little bit and start talking about this probability intersection theory. And maybe at the end we can talk about some of the pros and cons using this versus the traditional method of MCMC sampling. So before I introduce like the actual theory, the math behind all of this, I just want to zoom out really far and just think about what are we doing when we're formulating inverse problems with geophysics. So really what we're doing is we're combining sources of information. We have two main sources of information. The first source of information is theories or priors. This is like, in our heads, this is what we understand about the, system that we're working with. And so we can represent the theories or the prior as probability density of its own. So if we represent the theory as a probability density theta of our model parameters and our data, we could write that as a probability density, which is just kind of shown by this outlined, gray area here in this plot. So this is like a conceptual plot where we have our model parameters on one axis and our data parameters on the other axis. And so we have a joint probability density in the model and data space here. And then we can represent our theoretical understanding in that probability density. And then we go out in the field and we collect data. So these are our observations or our measurements. We can represent these as a separate probability density row. And that's kind of shown in this other gray blob here. And then when we're doing inverse problems, really what we're doing is we're saying, all right, we have an understanding of what's under the, in the subsurface. And then we also have data to back up those, the theories. The inverse problem is the intersection between these two sources of information, or the combination of these two sources of information. And so the way that we can write that is we can say that the posterior of our model parameters and data variables is really just the intersection between our theories and our measurements. And so visually what that's saying is that what we need to do is calculate the intersection, the overlap between these two probability densities here, where this little upside down, or not, this little almost triangle operator or triangle symbol here represents the intersection operator that finds the overlap between the two probability densities. And so what's difficult with this is that the posterior in this form is not written in the way that we normally think about posteriors. So this is not the probability of M given D. We are not using this. We are not starting from a conditional probability when we're doing inverse problems with this format. We are starting from the intersection of two probability densities, two separate probability densities. So this is really hard. I mean, this is why it's taken me like years to get to this point, is because I've had to retrain my brain to think about inverse problems, not as P of M given D, but as the intersection of two probability densities. So that's like a big challenge of communicating some of this work here, is that we can't think of the posterior as P of M given D. We have to think of it as the intersection of two probability densities. And so now that we've formulated what we're doing with the inverse problem, we can assign some math to it. So again, this is the same plot from before, where we have our measurements and our theories, and the posterior is the intersection between them. The way that the math of that works out is that our posterior is equal to the product of our theory multiplied with the measurements, and divided by this mu, which is this homogeneous density. This refers to like an uninformative or minimum information probability density. I'll talk more about this in like 2 slides, but for now, just assume it's a thing we can calculate. And so, and then you just have this K value here that makes sure everything sums up to 1. But the main point is that we have a product of probability densities here, and then we just divide by the homogeneous density. And so now what we're going to do is we have this math that we can solve the inverse problem with. We're going to go through and we're going to rederive the Bayes factor in this new new framework. And this will be important later on because it's going to help us simplify the inverse problem some. And so the way that we do this is we just write the posterior the same as before, but now we introduce this H term for hypothesis. And so it only shows up in the theta because we don't have measurements of H. And so we use this form to write the posterior odds. The posterior odds is just the ratio of one hypothesis to another hypothesis. And then that works out to be the ratio of the prior probability of those hypotheses multiplied by the Bayes factor, which is B. And then the Bayes factor has this nasty form here with there's integrals on the top and the bottom. And so we're going to go and we're going to simplify that in a second here. And the way that we simplify that is by introducing this idea of a null hypothesis. So this is a very, very general null hypothesis. This can be applied to, in theory, any type of data. The null hypothesis is necessary because, again, everything is relative to something. So the null hypothesis gives us like a baseline to compare any sort of model to. And so a good baseline would be an uninformative model. The idea being if the data are better explained by an uninformative model than our own theories, then our theories are wrong. So the way that we write that is theta of D given the probability density of our data given our null hypothesis is equal to this uninformative density. And so this is related to the Jeffreys prior. It comes up all over the place, but for our purposes, just know that there's different ways to assign this, and it's going to depend on what kind of data you're working with. So if your data are real valued, they could go from -infinity to infinity, then you'll have like a constant. If you have a positive number, so things are like our electrical resistivities, our densities, things like that, where you have a bound at 0, then you get this 1 over x behavior. If you get if you're working on the surface of a circle or a sphere, something that's closed, then we can get, use like the geometry of that space to get out the probability density. And so this helps us simplify the Bayes factor to this form. So this is the Bayes factor of any hypothesis relative to the null hypothesis. You can see it's a lot simpler now. It's just a product of a few probability densities. This is just a good way to think about what the Bayes factor is telling us. This is really what's important. If you've tuned out from all the math, I'm sorry, but now you can pay attention. This is what the Bayes factor is telling us. So we have 3 examples here of different scenarios with the Bayes factor calculated. On the left here, we have an example where our model and our data have overlap. So the blue contours represent our theoretical probability density of our data. The black represents our measured probability density of our data. And because there's overlap, we get a Bayes factor greater than 1. And then we could call this an unfalsified model. On the other extreme, we have no overlap between our measurements and our theory. We get a Bayes factor way less than 1, and we would call this a falsified model because we have a disagreement between what our theory is telling us and what we actually see in reality. And then, you can also imagine you have this overlapping case where you have a Bayes factor greater than 1, and so if you got something like this, you'd have to think a little bit harder about what it is that you're getting right and also maybe getting wrong in your model. And so where this is important for inversion is that it helps us solve this problem of what happens if you get a bad model. What happens if you try to do inversion with a prior that is totally wrong and doesn't agree with your data at all. And so there's a solution to that in this framework here. And so the main properties that come out of this probability intersection is that if you have an unfalsified model, again, where you have overlap between your model and data, then what happens is the posterior of your data is just equal to your measurements. And this is good. This is what we would expect. We don't have any change in our measurements, which means that our measurements are real. Like, you don't want your measurements to be updated in the posterior distribution. So if you have an unfalsified model, then your measurements stay the same. That just works out in the math. And then similarly, if you have a falsified model, you won't get any update to the model parameters. And so instead, what's going to happen is you're going to get an update to your data to compensate for your model and your data being totally inconsistent with each other. And so what's important from here is that we can use the unfalsified, if we assume an unfalsified model, we can simplify the inverse problem down to this form here. And so I'm going to talk a little bit more about this form on the next slide here. Just note that the G of M represents some forward model that we use to simulate our data. So this could be like simulating seismic from, I don't know, a set of, a subsurface model or anything that you want. And so here's the difference between the normal way of working with Bayes rule and this formula that we just came up with in the probability intersection. And they look really similar, right? There's 3 terms, and some of the terms are really similar. So in the normal way of working with Bayes rule, we have this likelihood function, we have a prior, and we have this bottom term here. This is called a marginal likelihood. Usually this is too hard to calculate, so we just ignore it. And that's why we have to do sampling. But in the probability intersection framework, what this tells us is we have the product of our measurement density evaluated at some forward model data multiplied by a prior. And then we also have this forward modeled density from our data. So this is a little bit stronger interpretation of what this than the marginal likelihoods. We can calculate this data is what I guess I'm trying to say. And the biggest difference here, and it's really subtle, but it's a huge difference, is that there's no conditional probability on the right-hand side here. There's no conditional probability. So what that means is it's going to affect how we're able to estimate probability densities. So what's going to end up happening is that without the conditional probability in this term, in this equation here, we can actually just go ahead and calculate posterior densities directly. And so to give a visual interpretation of what this difference of having a conditional probability versus not having conditional probability is, there's a nice diagram here that shows this. So what you're seeing on this diagram here, the x-axis is our data variable, the y-axis is our model variable. What we've done is we've come up with a prior in our model space that's shown by this blue here, and we've just sampled from sampled M from that distribution, and then we've just used a sine function, a sine wave, which is why you see the wave here, to calculate the data. So we say the data is a sine wave of our model parameters, and so then you can fit this the data, the distribution of data here, that's shown in blue, and then what we do when we do conditional. Oh, sorry, I forgot one step. We've also had to add measurement error in. We add measurement error in using this likelihood term. And so then when we are doing the inversion, what we're saying is we take our observed data, D, which is this vertical line here, and then we go through, we estimate this density, and we get the posterior, which is again the red here. So we can see the multiple modes being captured. But what we've really done is we've taken our measurement error and we've put it into our forward model, which is why we see the spread in the scatter plot here. Now, the difference between this and what we're doing in probability intersection is that we're treating the measurement error as an entirely separate distribution. So this is the same plot, except that instead of adding measurement error into our forward model, we get this nice, perfect sine wave here that has no spread around it. And our measurement error is in an entirely separate distribution, which you can see on the bottom here. So instead of a vertical line, we have a spread out distribution. So what we can do is we can just pull each of these model parameter samples, and then just we have the distribution of the data in the red here. We evaluate that, then we multiply by the prior, and then we divide by this theoretical density in blue here. So we treat measurement error differently, and it results in a different form that is we can use just calculate probability densities directly from. And so essentially what we've done is we've turned the sampling problem into a density estimation problem. So there's a simple algorithm for how you can do this. You can run Monte Carlo on your forward model. So what you essentially do at the first step is you're generating a set of realizations from your prior. So you have, you can represent those in a matrix if you want, where you have a set of model parameters, a set of data. You can generate many realizations of that to start with. And then once you have your data variables, you can just go through and you can estimate your probability density of your data, and then evaluate those densities at each step. And so, now at this point, we have all of our densities estimated, and then for each realization from our prior, we can evaluate all of these different individual probability densities, and then we just multiply them together to get the posterior. And so this is how it's going to be done in practice. And so what this means is that what we can do is just estimate probability densities and then multiply them together for different realizations. And in this way, we don't have to worry about any Markov chain Monte Carlo sampling. Every model that we simulate can be used for the inversion. And so the real key here is okay, we still have the problem of high dimensional probability densities, but the key is that machine learning it can help us go from high dimensional data variables down to low dimensional data variables. So what we're saying is we're taking our data vector here, we're finding a function S that takes in a data variable and spits out a low dimensional summary statistic. That's why we're calling it S. And so it's easier to do density estimation in low dimensions. And so the key here is that we can use machine learning now, or other methods, regression methods, whatever, to find a function that finds an informative summary statistic out of our data. And so this is really the key now, is that we can do all of our forward modeling, use machine learning to find informative statistics, and then just do inversion right away. And so the limitation here is just how hard is it to do the density estimation instead of any sort of computational expense. And this is also why it's useful for hypothesis-driven inversion, because we can fit a machine learning model that is informative of the few statistics or few parameters that we care about, and then we can estimate those pretty easily without going through MCMC. Where this is going to fail is if we do care about high dimensional models. So if we care about, for example, getting a pixel-based map in the subsurface and getting uncertainty on that, this probably won't be that effective. It's going to be more effective at learning a handful of parameters and then doing density estimation on those parameters to find posteriors. But what we've done is we've lowered the bar for computational expense. And so at this point, I'm going to transition over to like a real world example. I know that was kind of like an information dump, so I'd like to give you guys a shot to ask any questions before I just run through the last few slides of the example. If anyone has anything they'd like to chime in with. All right, that's okay. I will just move on then to a real world example. So this is, again, from some of the work that we did in Colorado that I showed on the title slide. And the motivation for this was we had a few sort of data sets here. On the top, you see this is inverted airborne EM resistivity. We have a cross section of ERT that goes through this area here and a couple of wells. If you look, there's like this blue linear feature here that's electrically conductive, and then that shows up in the geophysics down here. So again, this is our inverted ERT section on the bottom. On the top is a geologic cross section from a geologic map. We see the anomaly shows up both in the airborne EM, the map view, as well as penetrating into the subsurface from the ERT cross section. But interestingly, we don't see a whole lot going on in this geologic map here. This is from like the 90s, so there's been a lot more data that's been collected since then. But the initial people studying this area didn't notice anything on the surface. So there's also some well data, and some of the cores through the wells show that this conductive anomaly has fractures. Outside of the conductive anomaly, this is shale that's like really competent. And so the idea is this anomaly is electrically conductive because it has fractures and because it has a higher porosity, it has a higher water content that drives down the electrical resistivity and makes this show up as this blue electrically conductive zone. And so what we're going to try to do with this is we're going to try to figure out what's causing this. And so we had a couple of ideas of what's causing this anomaly, and so those are outlined here. One thing that could have been doing it is just bedding planes. So for whatever reason, there's a layer of sediment deposited in the shale that is more conducive to fracturing than the outside shale. So that's one idea. Another idea is that a thrust fault because there is faulting. It's a mountainous area. A thrust fault could have come up and cause this fractures. Another idea, I mean, similar to the thrust fault, but more of like a high angle normal or reverse fault. And then finally, because there's glacial features in the area, we hypothesize that it could also have been a tension fissure. So this is from the glaciers melting, releasing stress, and then pulling the crust apart as it responds to the offloading of the stress. And so, those are the four basic ideas. The thrust faults and the reverse fault could dip either direction. We don't really know. But the main idea is that the main difference between these four processes that could have created this zone is that there is a difference in the dip angle of this layer. And so we can't really tell from this plot here what the dip angle is. And so this is where this idea of hypothesis-driven inversion comes in handy, is because we want to take this data and we want to find the dip angle of this layer. So what we do is we come up with this prior model. It's just a layer. It has a thickness. It has a position, which is X. It has a dip angle, which is the phi. And then there's electrical resistivity on the outside, rho B, and then resistivity on the inside of the fracture zone, which is rho F. And we assign uncertainties to all of those, and we can come up with all of these different subsurface models, which are shown. 4 of them are shown down here, where you have different combinations of dip, thickness, location, resistivity values. And so we have this collection of models down here, and we're able to simulate 2,000 of them by taking a set of model parameters, running our forward model, and then we have our geophysical data. So we have a set of model parameters and we have our geophysical data. Nice thing is this is all done in parallel, so we're able to use like 50 nodes at one time to do the simulation. And it actually doesn't take that long. It only takes like less than a day to get 2,000 of these realizations on that many nodes. And so now we're going to go through and we're going to do this hypothesis test, because this is important to know if we have a good prior or not. And so the way we do it is we're using this dimension reduction technique, principal component analysis. So we've taken all of our data and we've projected each one of our realizations into a single point in this reduced dimension space. You can see these 2 principal components almost account for like 90% of the variance. So what you can see is that each of these small dots are realizations from our prior, which look like this, where these are the electrical resistances like normalized and projected onto a space. And each one of these represents to a different dot on this reduced dimension plot here. And then we could fit a density to that in that reduced dimension space. And then we take our measurements, which are shown here, it's projected in the same dimension space. Here's our zone with the anomaly circled in black. We have error estimates on the measurements, which we can then use to project into, again, this low dimensional space. And then we can calculate the Bayes factor from this. The Bayes factor turns out to be 2.2, which is greater than 1, which means, okay, we have a prior that's doing a reasonably good job of representing the data that we're interested in. And so now what we do is we know we have a decent prior. We train a random forest to actually take in a set of data and then predict the model parameters from that. And so essentially we have 5 random forest models, which are, you call it what you want, but really the 5 random forest models together are one big machine learning model. And so what we've done is taken this high dimensional data D in our geophysics. We've fit this statistic S that gives us a low dimensional representation of our data that informs the parameters that we're interested in. So we've gone from a high dimensional density to a low dimensional density here. And so once we've done that, pretty much our job is done. we can go and we can apply this equation for the inversion, and boom, now we have our inverted model parameters. And so this was done without MCMC. It's pretty straightforward. You just do your data, fit a machine learning model, implement some kernel density estimation or whatever you want, and then you're done. And so this is the results. This is what it looks like. The black lines are the priors, blue are weighted histograms, because again, we have not samples, but we have probability densities. So this becomes like a weighted histogram is how we represent it. But you can see not only marginal probability, posterior probabilities on the diagonal have been updated. You can also see some correlations in a few different parameters that we've been able to capture by this method. And so again, for us, the most important thing was the dip angle. So we're able to use this and say that the data that we have is most consistent with either something dipping steeply to the southwest. In this case, it was most likely either a normal or reverse fault or a sedimentary layer. We were able to rule out the idea of it being a thrust fault, and we were able to rule out the idea of it being this post-glacial tension fissure, which in our case was really important because it's helped us understand the subsurface in our model domain much better, and we've have a deeper understanding of the geology, which helps us understand all sorts of watershed processes. So that's the end of that example there. I'm going to leave it on this slide. The key point that I want to just, if there's one take-home message, just know that this hypothesis-driven inversion technique, it helps us measure specific parameters that we want to get out of geophysical data, and it helps us do it in a way that doesn't require going through MCMC sampling. We can just do highly parallelized Monte Carlo simulation, and then use machine learning methods to find informative parts of our data that help us do our final inversion. So yeah, I'll leave it on this slide. These are just a few of the key figures from the talk. So feel free to email me here if you're interested in. I'd be happy to talk more about this. I'm super interested in all things, geophysics, inverse problems, whatever. Please feel free to reach out to me. And at this point, I'll stop, and I am more than happy to take any questions from you guys. So thank you for listening.
Awesome. Thanks, Alex. Feel free to unmute yourself if you have a question.
I think I have one. That was an awesome talk. So you have your principal components on the left in this slide.
Mm-hmm.
So is that basic, I guess, what's physically are your principal components? Is it the parameters that you have on the right then?
Good question. The principal components, I have a better plot, just not on these slides here. The principal components go back to the data. So the principal components really show the variability in the data that we simulated. So that would be, we can plot the principal components like this, and it shows like cool variability in the data. It's hard to explain, but if I had a picture, it would make more sense. It might not be super satisfying answer, but
no, that clarified a bit. Thank you.
I have a question. You said you were able to parallelize this method of it. So like, what is sort of the timeline from you went and collected your electrical resistivity data, and then kind of how long does it take you to get your posterior distributions?
Good question. The hardest part is getting the forward model set up. The hardest part is getting a model that takes in your parameters and spits out something that looks like your data. That's the hardest part. Once you've done that, everything else is easy. You know, a matter of a few days maybe, because now we have codes and stuff too that can just, you know, you run the everything in parallel. We have codes that does all of that. The hardest part is for each problem, you're going to have to set up a different model. And that is not a problem that's unique to this, but is a major challenge still.
Cool.
Okay, sorry, one more. So you had in a slide you showed like, was it 4 basic like hypotheses?
Yeah.
Yeah, so in reality, it's not these 4, but also like the sweep of potential parameters that can describe these 4. Is that right? So that's like kind of the benefit of this method.
Yeah. Yeah. These were the 4 that we were most interested in. In reality, what we've done is we've just inverted a model, a simple model that's just a dipping layer.
Beautiful. Okay, thank you.
Any other questions? All right. Thanks, Alex. That was super informative. Thanks for presenting.
Yeah. Thank you guys for having me. And yeah, follow up if you want. Happy to talk, but if not, thank you anyway, and hope everyone has a good rest of their day.
You too.
Thanks, Alex.
Thank you.